Okay, I'm Ray Rosligi. I'm from Quantitative Neuroimaging Laboratory in Columbia. My talk, I'm going to talk about the spatial processing. The way I assign this is that Frederick Blaise will be talking about the temporal processing, and I would do spatial processing. And the point of these two talks is not about talking about what is the best or state-of-the-art theoretical models to solve these problems. It's just to make you guys familiarize with the problem. So there's these quote-unquote terms in the field, or in pretty much 90% of the paper that I read, it says, we use standard preprocessing technique. I hate that sentence. There's no standard preprocessing technique. In fact, there's 14 million different ways you can preprocess your data, and the problem is each of them gives you different results. We already did this in one of our reports to NIH and said, we just listed the number of parameters that you can change in the preprocessing, and it ended up to be 14 million different way of doing this. So in my talk, I will, the other one? Okay. So I will just focus on the concept, why is it that these steps are needed, and I will also emphasize a lot on the fact that when it is not needed, because lots of time I've seen my students, they come and do these processes that they have no idea why they're doing it. It's just they say, oh, in most of the paper they're doing it, but every fMRI study has its own requirement and it has its own spatial treatment. Therefore, you can't just come in and follow a default pre-processing pipeline just because everybody else is using it. So I'm going to talk about when we don't need these steps, and if we need it, how is it usually done, and if we have some empirical evidence which one is outperforming the other one, I will talk about it. And I will only focus on 3 spatial processing: spatial realignment, which is called motion correction, which is I don't agree with that. It's just a realignment. Then I'll talk about the geometric distortion and then the spatial normalization, and at the end I finalize with the smoothing. So why is it needed? Subject moves in the scanner, whether you want it or you don't want it, whether even himself want it or don't want it, it's going to move inside the scanner. But the scanner doesn't. The scanner is like 5-ton equipment, doesn't move. So therefore, what happens is when you're recording an fMRI data from a very specific location of the brain, that signal is going to change to a different part of the brain if the subject moves, right? Therefore, you need to somehow correct these things. Probably it's the most damaging and frustrating problem associated with fMRI data because we still don't know how to solve it. Resting data are much more vulnerable to it, and I'll talk about why they are more vulnerable to it. And the other step is realignment, which I'm going to talk about it, is not a motion correction, is the one part of a motion correction which corrects some specific type of motions, but it doesn't remove the effect of motion from your data. After realignment, you still may have lots of motion artifact in your data. So I call it as one step toward the correcting it, but it's not a motion correction, it's just a realignment. I always have this terminology, semantic argument with my students that they call this motion correction, but it's just a realignment, one step for motion correction. And it does not correct all the artifact caused by motion, as I just mentioned. So what are the artifacts of motion? So let's go through these steps one by one and see what are the artifacts can be generated by motion. So the first one I already talked about it. So the first one is just switches the recording of one voxel to another voxel. Let's say if the subject in ideal situation moves 2 voxels up, right, at that location, that this is a frame-wise displacement of the subject. I just intentionally picked up this real subject. He was pre-stable inside the scanner and suddenly start dancing at this part, and then start stabilizing. Maybe they played some music for him inside the scanner. I don't know why, but that's what happened. So if you look at one particular voxel, you see this. You see clearly that something was happening there, and then just jumped down and went to another intensity level, and the rest of the signal started from there. And that's what the first thing that everybody was thinking is happening. But it's also changed the slice orientation. When the subject change or rotate his head, the slide that we're acquiring, it's going to stay the same. So when the subject move his head, the slice orientation is going to change, as you can see here. Like if you were acquiring the slice in a horizontal fashion, when the subject head is moving, so the slice orientation is going to change. The other thing that we just talked about it with Blaze's talk is it's interact with motion. So in the beginning of the volume, the slices are acquired in a horizontal way, and the moment the subject moved, slices are acquired in a different way. So, and this is for interleave, and for even odd interleave. If it's another order of interleave, that's even going to be worse. And the last one, which I think is the most important one, and it's always missed in the whole explanation of the motion, is the distortion of the homogeneity of the magnetic field. So when the subject head moves inside the scanner, even very slight movement, that's going to distort the magnetic field homogeneity. It means to be able to acquire data from the scanner, we need a very, very homogeneous magnetic field. If that homogeneity somehow changes, your signal is not usable anymore. And as you can see, this is, again, the same data, same subject, just looking at different voxels. And as you can see, the effect of the motion on the different voxels are completely different, right? Here, it jumps down to another level, and it starts following from there. Here, you have a very sudden drop in the signal. And in another voxel, you have a very sudden peak on that location. So this is also bringing up another issue that the effect of the motion on your signal is not linear. Just because you have a frame-wise displacement that jumps up at that location, it doesn't mean your signal is going to jump up or jump down, or it's going to go to another level. Any of these can be happening. And that's why most of the linear techniques are failing. You can't just put 6 motion parameters inside your design matrix and assume that everything is gone. Yes, the linear effect of the motion will be removed by doing that, but not the rest of them. And if you look at the frame-wise displacement, the linear effect is going to be this one. This voxel might be slightly corrected with putting the motion parameters inside your design matrix, but the rest of them will not. All right? So let's talk about the interaction with motion. I made these slides for my class, so I'm just going to show it to you guys. So as you can see, this is a interleave parameter 1, 2, 3, 4, and then if the subject moves 10 degrees, right, within the TR, in 1/3 of a TR, some of the other voxel, other slides are going to orient it at this rotation, 20 degrees, and if you combine them, that's how it's going to be in your, the final slides are going to acquire. So as you can see, even though the motion is happening slightly throughout the TR, the whole slice acquisition is all mixed up now. That's why we can separate it easily, the effect of the motion and slice timing correction. That's why nobody can come and say which one needs to be done first, because they're happening at the same time. They're affecting your signal at the same time. So you can't separate, you can't say which one I have to do first and next. And that's why empirically nobody has been able to find any good, valid data to support which one we need to do first. Okay, now the point is when it is not needed. So unless the subject is not moving, unless you're acquiring anesthetized, actually anesthetized subjects are also sometimes moving. Unless the subject is not moving, you have to do it, right? So realignment assigns the correct signal to each voxels after motion, right? So it's only fixing the first artifacts. The rest of the artifacts are still going to remain after your realignment. Distorting magnetic field generates a spatial distortion, which also reduces the accuracy of the rigid body registration. As all we know, realignment relies on the rigid body registration. Realignment before or after slice timing correction may reduce its effectivity, so we don't know which one to use. And realignment itself may induce functional connectivity in resting state data. I'll talk about this a little more. I have some example for this last item. Different type of motions. So to understand the motion problem in fMRI a little more, you have to consider the fact that there are different motion, right? There's a motion to the, due to the sudden head movement. Subject inside the scanner gets tired and he wants to move, and that's pretty much the most often motion that we see and we want to correct for. Motions due to the respiration. So it causes respiration, breathing inside the scanner, because we don't breathe in the same rate all the time. After a few seconds, or maybe, I don't know exactly how much, we have one big breathing that affects as a movement inside your head involuntarily, and that's caused, you can see it in your motion parameters. The other effect of the respiration is the variation in the volume of air inside the lung, which distorts the magnetic field, and that's another thing that we see. Motion to the tremor in elders. Old people usually have this shaking effect inside the scanner. And the last part, which is the most frustrating part, is the task-related motion. Depending on what task you have, if you're asking a subject to respond, as you will see, or you may have seen, every time the subject is responding, his head is moving. And that's the worst kind of motion you may see. Or sometimes they don't even move their head, they are breathe. Every time they want to answer, they make a deep breath. Deep breathe, and that's the motion. And the fact that they are correlated with your task, if you regress them out, as linearly lots of people do, it's taking out all of your effect as well. So lots of type 1 error you can see in that problem. So these are the type of motion. So you need to understand what kind of emotion you're dealing with, right? So before start attacking to it. If you don't know what is your motion and what is it causing it, just applying a motion correction or realignment is not going to solve your problem. So how's it done? So far, the most effective technique that I have seen is to prevent it. So try so hard for your subject not to move. Usually, we put this little tape, we tape the subject's head to the coil. You can't imagine how much that helps for the subject not to move, because usually they don't have any reference. They just put their head and they move. But this tape somehow stretch their skin or something, so they have the point of reference, so they don't move their head inside the scanner. But there are other techniques. These are from Hootel's book, so you can, some of them, they have this bite bar. If you're not interested in the area of that they get activated with the bites, you can use this one, but you have to be cautious that the area that activating your bite in your brain is going to light up in your scanner if it's related to your task. And then the other one is put some cushioning, enough cushioning inside around the head. If the subject doesn't get claustrophobic, I would get. So I haven't seen anybody can use this. And then this other one is also effective, which is the inflatable cushion. So you put the cushion around the head and inflate it, and that's actually a very good technique to make them stable. So, but we all know, we all deal with the data which is already acquired. So how to solve this problem after acquiring it? So it's, oops, what did I do? So we usually do it by registering the fMRI volumes to the reference volume. The reference volume can be T1 or T2 images. And in both cases, if you're using modality, you have to remember, always use information theoretic measures. Use 6 degrees of freedom. Always trust the header of the fMRI, header of the data more than the registration. Registration is an optimization problem. Never gives you a better results than actual measurements that comes from the file header. So I've seen lots of people, they use more than 6 degrees of freedom. Which volume to use? You can use also one volume from the fMRI data to use your registration. You can also average the fMRI data to do the registration. And this figure actually shows very clearly. So this is your subject. You can choose one of the fMRI volume, structural image, or skull stripped one. So if you're using a structural image, at least try to skull stripping before doing it. So you can see this is much more similar to the fMRI data. So this registration is going to happen well. But as you can see, these are different modalities, so you need to use information theory techniques instead of typical cross correlations. So it is suggested to use fMRI temporal mean volume or single volume as a reference image. So if you want to be very savvy in the realignment, what you can do, you can do first level realignment, just a very raw realignment with the middle volume, inspect your frame-wise displacement, and see in what area you almost have no movement. The subject has less motion. And then select those area and average those volume, and that would be your reference volume. And then you can correct with that reference volume instead of just picking it randomly in the middle of the slides. Because if you pick a volume which is actually acquired during the movement, that's going to cause problem. That's going to reduce the effect of realignment. So you need to select a volume which is robust. So if you average the entire time series, that also be generating the very robust volume to register. But the point is, if you do that, if the subject moved a lot, that will be actually a very problematic case as well. So if you know your subject is pretty stable and it didn't move much, you just simply average all the volumes. No matter what technique you use, after motion correction, you have to look at your data. Looking at your data is the first things fMRI data analysis has to do it. Just because you have too much data, it doesn't mean you should not look at your data. I've seen people, they done studies with data which literally everything is zero, or literally everything is the same volume, right? So please look at your data. It is very important. Visual inspection is the first things that you do when you do fMRI analysis. This is another interesting point. Which interpolation? As I told you, there's millions of parameters that you can change while you're doing this realignment. So I did this very, in one of my talk, a student asked me, what is the effect of interpolation? And that caused me to go and do this simulation. So in this simulation, I put random noise for each voxel. Right? Every voxel here has a completely random noise on it, Gaussian noise. And I put a seed in the posterior cingulate, and I compute the correlation between this random noise inside the posterior cingulate and the data itself. And I induced motion by applying motion parameters to the data and shifting the brain up and down. And then I did motion correction, right? And when I was doing motion correction, I used nearest neighbor interpolation, and I used linear interpolation or trilinear interpolation. And that's how you see how much you see a correlation induced by trilinear interpolation. And the effect is, the reason is very simple, because any kind of interpolation that you do, it acts like a very slight smoothing. Right? So what happens is you have two random noise, right? Now try to smooth both of them. You will induce correlation between them, because smoothing is going to reduce, it's going to low pass your signal, and that will create some correlation between them. And then a quick demonstration of why resting bowls are more vulnerable to the motion. So the difference comes from the fact that how we process this data. If you have a task data, you have an onset, offset of task, you come involved with this, let's assume you're doing a simple GLM analysis, you have your regressor, and you regress your fMRI data from your regressor, and you get the activation, right? And now let's assume the subject is moving, right? Let's assume at this point, right, a subject moved. What will happen to your regressor if the subject moves? Nothing. The regressor is always fixed. Your predictor doesn't change when the subject moves inside the scanner. It's always constant. Now, let's go to the motion, to the resting state data. So what happened in resting state data? You have a seed signal, right? And you have a bunch of other voxels. So if the subject moved at this point, your predictors also moved. And that's the whole problem. Your predictor is inside the brain. So whatever global artifact affecting your brain is affecting both the predictor and independent variables. That's why you see all these artifacts in your data. And that's what it's more vulnerable to the analysis. I did another interesting simulation for one of my students. In this simulation, I put same underlying regressors, or let's say same bold signal for 5 different regions inside the brain. As you can see, posterior cingulate, orbital, medial orbital frontal, superior temporal, superior temporal, superior frontal, and I don't know, and then supramarginal, right? So, and on the left hemisphere, I put all random noise. Everything is random noise. And I process the data. As you can see, these are very clear data, and I saw very nice connectivity between all of those by putting seed on the posterior cingulate. What happens after adding motion? Now I apply motion to this subject, and the seed is still posterior cingulate, and that's how you see how much connectivity is induced by applying motion to the data. This shows what devastating is the effect of motion on the subjects, and you have to do motion correction. The problem is when you do motion correction, everything is gone. And remember, this is not motion correction. I made a mistake again. This is realignment. Once you did the realignment, lots of artifact goes away. But it also, your effect, the effect that you're interested goes away. This is something never been explained. Lots of people, they try to remove motion by scrubbing 20 seconds before or 20 seconds after, but nobody talks about what will happen to your actual effect. And unless you simulate these things, there's no way you would find out this. Now, in the next slides, I'm going to show you guys, let's move the seed region to the right hemisphere, which is all noise, right? If you remove the seed to the right hemisphere, you see a bunch of false positives. You add motion. This is what is called coloring. What happens is somehow, which I don't understand why, it's been reported many times, that motion adds coloring to your noise. So as you can see, the bottom of the sulcuses, they become negatively correlated with the seed region, and the top of the gyrus, they become positively correlated. And after motion correction, nothing happens. I mean, after realignment. So the realignment does not do anything for this kind of effect. So you have to come up with different solutions for this problem. So this, all I'm trying to show you guys is that realignment just solves the problem of voxel shifting to another location. It does not solve the rest of the motion artifacts, right? So I have to move a little faster. So the next topic is the geometric distortion correction. So why is it needed? What is geometric distortion correction? So this is the effect of magnetic field inhomogeneity. by why magnetic field inhomogeneity generates spatial distortion. As most of you guys would know, the spatial information are encoded in the phase of the data, right? As you can see, and then this the distortion in the magnetic field is going to change the frequency of the MR signal, and that will be translated back to the location of the voxels. So in this figure, you can see the border of two different fMRI data on top of a structural image. And that's what is called spatial distortion. It means the brain is somehow stretched on different direction or pushed into in different direction, and that's what is called spatial distortion. If you guys know my friend Jim Brewer, you would know he doesn't look like this. This is the Jim Brewer that I know. So that's actually, this was a very smart way of showing the effect of spatial distortion. So spatial distortion, it's actually push the brain toward the center on the bottom and top part of the brain. And another figure that represents the problem. Remember, I'm just representing the problem for now. So if you have an EPI image, you have a field map, and when you correct, this is the corrected data. So I hope it was clear what is spatial distortion. When it is not needed, if the study doesn't need a functional structural image co-registration, you don't need it, right? What does that mean? So it means if you're doing a spatial normalization, indirect spatial normalization, it means your spatial normalization is directly registering your data to the template, you usually don't need it because you don't need to map your fMRI to a structural image. Therefore, you don't care much about this correction. And that's why most of the people don't do this. Actually, I have to correct myself. Most of the people don't do it because they don't have the field map. But yeah, that's what it is. If the distortion level is very low due to the high quality of the scanner and its calibration and shimming, you usually don't need to do it. Like if the data are acquired in very well maintained scanner, usually you don't see a very bad magnetic field distortion, especially in 3 Tesla, typical, not multi-banding, typical fMRI analysis. You won't see such a high spatial distortion. How's it done? Again, it's done with shimming coil and magnetic field mapping. So shimming coil are done during the acquisition. Field mapping is the post-processing. So shimming coil accounts for the inhomogeneity in the magnetic field before starting the acquisition. Magnetic field mapping is simply acquiring data with slightly different TEs with echo times. And if the echo times are slightly changing from each other, the only effect you see is in the phase of the signal is going to be due to the inhomogeneity in the magnetic field, because you don't let the net magnetism to change much. So all you see is the effect of inhomogeneity. So which method to use? Pretty much SPM, FSL, they have technique to use to import the field mapping and apply the data. But one thing I have to, based on my experience, is that if you're doing correction, check your data. Right? So you have to, if you're doing correction, you have to understand what this correction does. Right? Because there's lots of parameters inside this field map, the gradient direction, the direction that you change your phase encoding, and if you're away from the scanner or you're doing this on the already acquired data, these parameters can be completely wrong. You might be selecting these things wrong, and you actually, if you do with any of these parameters in a reverse order, you're actually making the problem worse, not improving. And when you're looking at the image, and you're seeing after correction the image is changing, that doesn't mean you're correcting for it. Just because your image is changing after spatial distortion correction, it doesn't mean you're doing it correctly. You have to put it on the structural image and see if it aligns better after correction. If it gets worse, you're doing something wrong. right? So you have to do it. You have to check it and make sure that you're doing it correctly. And after correction, the registration performs a better fit between your functional data and your structural data. Does it make sense? So that's my quick explanation of spatial distortion. Let's move to the spatial normalization. There are two types of spatial normalization, localization or normalization. Localization means neuroanatomical regions are not completely visible in fMRI. So therefore, you need another technique to come in and tells you what part of the fMRI data belongs to which anatomical locations. And normalization is for it's for when you want to compare a bunch of people in your study to another bunch. Therefore, you need to put all the subject in correspondence to each other. Usually, they don't separate these two, but you have to understand that these are two different things, two different problems, and they have two different solutions for them. So when is it not needed? Spatial normalization can be excessively inaccurate. I'll show you guys a slide how inaccurate it can get, especially when you're comparing the age-related groups, like young and old subjects, or male and female. For localization, if the segmented or parcellation structural image is available, then normalization becomes a co-registration problem. Due to the same reason, it is not required for the ROI analysis. So remember, the spatial normalization is not required if you're doing ROI analysis. So I, as a person who does fMRI data analysis, always try to get away, especially in our group that we work with lots of aging data. I try so hard to stay away with the spatial normalization. And I'll show you guys in a minute why. And the last point I want to make here is that no matter how perfect is your spatial normalization, is not going to account for the difference in the cytoarchitecture of the brain. This is something that if you're submitting a method for the spatial normalization, you always hear from the reviewers that, oh, this technique is perfect, but it doesn't correct for cytoarchitecture. What does it mean, the cytoarchitecture of the brain? It means if the tip of central gyrus, exactly the tip of the precentral gyrus, it's moving your right hand or your left hand, right? In another subject, the voxel, a few voxel next to it might do the same thing. So they're not every brain correspond their functionality to the folding patterns or to the morphology of the brains, right? So there's a slight differences in the location of the functionality of the subject in respect to its morphology, and that's what they're trying to explain. But nevertheless, our problem, as I will show you in a slide, is much worse than that. We're not talking about 1 millimeter, 2 millimeter, 3 millimeter difference. We're talking about 10 millimeter difference here by spatial normalization. So atlas-based spatial normalization warps the, in this technique you have your subject, warps it to the template, you have the atlas, you take the atlas, use the inverse transformation and bring the data to your subject space. Inaccuracy of it, this is an example from this paper. So we have a subject with usually, this subject has a very special disease on the temporal lobe, and they're trying to register that to a template, and these are the different techniques that they use, and they show the results. So these brains are supposed to look like this brain. And when you're looking at that point, which is, I think, precentral gyrus, that should be corresponding to all of this, which is not, unfortunately. And again, this is a very worse problem with the person with the diseased brain and age. So it's just to representing to you guys like how bad or how inaccurate is the spatial normalization. As everybody thinks, we take the subjects, we put it in the standard space. It doesn't go to standard space. So there are direct techniques which you take fMRI data and you register it to the EPI template, or there's an indirect technique, and you take your fMRI data, co-register to a T1, and register the T1 to the structural template. Usually, this technique, if you do it correctly, it improves your registration. And the way to check this is very simple, is that there are always a brain mask involved with these techniques. And as you will see, if you increase the number of subjects in your study and you use the direct technique, the brain mass becomes smaller and smaller. And that shows how inaccurate is this registration. If you use this technique, the other indirect one, you will see the brain mass will also decrease, but it will decrease to a lesser degree than the other one. Which template to use? It depends on your study. Lots of people, they average their own subjects to generate their template. Which atlas to use? Again, it depends what area you're interested. If you're interested in this atlas, you can use that. Fortunately, these are all now available in the MNI space, so you can just use the MNI template and take all these atlases on the MNI space. That's very easy. Overfitting. So somebody asked me last time why we don't use the best nonlinear registration technique to match the brains, right? The nonlinear registration techniques are so advanced now that they can convert this microphone to that chair. They can convert, and you have seen this probably online or something. They can convert anything to anything. You can convert, I've seen they convert pizza to a lady or the other way around. So they convert anything to anything. So why we can't fix this? Why it's so hard to convert brain to each other? The issue with the spatial normalization is not that converting the brain to look like each other, is to convert the brain in a way that the corresponding regions fit to each other, right? And I'm going to explain why that is the problem. So this is coming from Brian Avon's explanation of the ANTS software package, and he has no intention of showing overfitting in this image. I'm taking advantage of the situation. So he nonlinearly registers the fourth focus to the beetle, right? And transfers these two to each other. But look at the bumper in the beetles after transferring to the focus. Do you see that black area on the bumper? If that's the label of precentral gyrus, that's going to fall on the postcentral gyrus, and that's going to label your postcentral gyrus as a precentral gyrus. That's simple as that. They call it overfitting. I hate the term. I call it misfitting because it's not overfitting. Overfitting is a good thing. Misfitting is what is it supposed to be? It's a better term, and that's what is the effect. I couldn't find a better example of this to explain overfitting and why we should not push our nonlinear registration to a much higher or more relaxed technique to feed the brain, because it's going to feed everything to any other things, right? Native space analysis, I'm a big fan of native space analysis. It doesn't require spatial normalization. You just take the subject, right? You parcellate the subject, you register the subject to the fMRI data, you take each region, you average, and you get a time series for that one. Makes life much easier. The issue with this technique is that you're destined to use our predefined ROIs, and sometimes one ROI cannot be explaining everything happening in different functionality. Like, for example, this is superior temporal. As far as I know, superior temporal has like, I don't know, 20, 30 functional units in it, so, but it's averaging all of them. If you're not interested in this ROI, you have to come up with different ROI parcellation to be able to extract these things. Anyway, and the last one is the smoothing. And so in this, why we need a smoothing? Because the spatial filtering removes the mismatch between the voxel size and size of the activation area. fMRI data has a spatial correlation. So blurring introduced by vascular system. So as you guys know, the bold effect has been is going to be blurred by the blood passing through your voxel, and cortical gray matter have a thickness about 5 millimeters, which is often falls within the more than one voxels. And the spatial extent of fMRI signal are often larger than the expected area. So these are all the data that we can that helps us or improves our the results if we do spatial smoothing. across subject-brain morphology mismatch also calls for spatial smoothing. This is what I just said, because the spatial normalization is not going to perfectly align the brain. We just blend it a little bit so to have a better result, so we won't get a lot of false positive. Increasing the validity of statistical testing, because the more we blend, the more our data is going to look like Gaussian distribution. When is it not needed? This is the important part. When you don't need spatial smoothing, the first thing you don't need is the ROI analysis. If you're doing ROI analysis, don't do a spatial smoothing, because ROI, it's you extracting the ROI from the right place, so no need for spatial smoothing. But the point is, depending on the activation size, if you're looking for a very tiny area inside your brain and you smooth your data, you're going to lose it. But if you have a bigger area, let's say you have a flashing checkerboard and you're looking for activation due to the flashing checkerboard, and a big extent of area is going to be light up, and then the spatial smoothing will improve the results. But if you're looking at the cortical columns in the primary visual cortex, which are apart about 1 millimeter away from each other, and they stack on top of each other, if you smooth the data, there's no way you're going to get those findings. So that's what's happened. So I'm actually have to wrap up. Christian is getting ready to kick me out. So how's it done? It's done with the Gaussian filter. And FSL does this nonlinear technique that separates the tissue types, and that's pretty much it. And that's an example of what the data should look like after spatial normalization. Thank you so much. Any question?
All right, we have. You see, I've given up to try to control Ray. He usually overruns, but we have time for one question while the other speaker gets ready.
Could you expand a bit more on the nonlinear registration, especially the downsides of it? Because that's actually new to me, and that's really interesting, because the one thing that I hear from colleagues always is like, switch to Dartle, try to make everything as extreme as you can. That's right. But it doesn't seem to be this way.
I did not say do not use nonlinear registration. I said do not use very strong nonlinear registration.
Just use it with caution. I mean.
With the caution, like you can, I think the default in FSL, Mark, correct me if I'm wrong, is like you use control points are 10 millimeter away from each other. So that's okay. Okay. So that would be something that I would use. And I actually tried it and I compared with lots of other nonlinear registration. That actually works better than the other ones, unlike other reports. So if you go lower than that, if you put your control points, when I'm talking about the control points in nonlinear registration, every point is become a degree, it become your freedom. It moves around. So when you space those control points away from each other, it means you're giving less flexibility to nonlinear registration to map everything to everything. You know what I mean? And that's what I would use. So I'm not saying don't use. Actually, nonlinear registration is good. It's better than affine registration. It just don't use very strong nonlinear registration to convert this microphone to the computer. That's what I'm trying to say.
Yeah, I think this is just the analog of the bias variance trade-off in general. You know, model fitting, even in normal regression, right? If you use too many parameters, you start overfitting and introducing variance.
Pretty much
anyway,
the same analogy. Yeah.
We have to move on, kind of.
Thanks.
Running. We started really well, but then
Sorry,
then now we're running behind.